Welcome to Center of Math series on topology. Today we're going to talk a little bit about separability. So first, some definitions. So we say X, some topological space X satisfies the first axiom of countability. If every X point in X, little x and big X, has a countable neighborhood basis. So this just means for every little x in X, we can find a countable family of open sets that contain X, such that any open set which contains X contains at least one of these open sets in this family. So the second axiom of countability just means if the space X satisfies the second axiom, it has a countable basis. So we have a countable set of open sets such that any open set in X can be represented at the union of some number of these countable number of open sets. And X is separable if it has a countable set in X whose closure is all of X. So as an example, the real numbers is separable because the rationals are countable and dense in X, so their closure is all of the real number line. So the real number line is an example of a separable space. So we can prove a space X which satisfies the second axiom must be separable. And so the idea is just from the space X and the countable base, select a point from each open set in our countable base. This is a countable set. And then consider the closure of this set. Note that the closure is a closed set, so the complement of the closure is an open set. And since we select a point from each open set in a countable base, any open set in X must contain at least one of our points, because open sets are the union of open sets in the base, which we selected points from. And so if the closure is not all of X, we have an open set which does not contain a point, which is a contradiction. And so the closure must contain all of X. And so X must be separable. So, quick definition, a space X is called Hausdorff. For any 2 points x, y, and x, we can find an open set of X containing X and an open set containing Y, and the intersection of these two open sets is empty. And that's for any 2 points. We can select any points X and Y, and we can find sets that satisfy this property. So we can show all metric spaces have to be Hausdorff. So take a metric space, take any 2 different points x, y in our metric space, take 2 open balls of radius distance x, y over 3, one around x, one around y. Now we just need to note that the intersection of these 2 open balls has to be empty, because if it's not empty, we have some z that's contained in both these open balls, and so z, distance xz, is less than distance x, y over 3, and less than distance x, y over 3, and distance yz is also less than distance x, y over 3. And therefore, distance xy is less than or equal to distance xz plus distance yz, which is less than 2/3 distance xy. And this is impossible, as distance xy is a positive real number. And so we can't have any Z, and so these have void intersection, and so the space must be Hausdorff. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.